Hi, my name is Rob, the group leader for this project. Fellow group members include Peter, Suhail and Lachlan. Our primary objective for this project was to provide the client with a UAV plane. The client specified additional requirements to meet. These included unassisted takeoff, ability to do a figure 8 manoeuvre, to carry a ping pong ball and dollar coin. Some additional recommendations from the client were for the budget to not exceed $200, for the aircraft to be able to fly for 2 minutes and to be around 100 grams in weight. The plane was developed through the process of aeronautical engineering.
Aeronautical engineering is the conception, manufacture and iteration of aircraft that operate in Earth's atmosphere. Scientific principles are applied in real-world situations to model the best solutions. Collectively, we are drawn to aeronautical engineering because we love learning and understanding how things work. We enjoy challenges, have interests in vehicles and machinery, and would like to pursue careers in aircraft design.
The project's engineering process started with research. Existing products, airfoils, and design configurations were analysed to inform our conceptual design. An industry expert was next consulted to offer any pertinent advice on our design. This, along with our research, formed the basis for our conceptual design. The conceptual design was then presented to the client for approval. The next major stage of the project was testing and improving until design met the requirements. It was then presented to the client.
The research that was completed helps inform our conceptual design. First, we investigate similar products already in the market in order to give us some perspective on what wing loading, chord length, wingspan may be used appropriate for our purpose. Research of components was then conducted to highlight the best configuration for our plane. Empennage style, landing gear type, wing plan form, vertical wing angle, vertical wing position, fuselage construction and propulsion configuration were all aspects that were considered along with our airfoil selection.
Selection of the airfoil was quite simple. We each found and researched a few airfoils that met the requirements of around 12% thickness to chord ratio and low camber of around 1 to 3%. Once the options were selected, they were analysed in XFLR5 software at the calculated Reynolds number of 30,000. Results of which were compiled into a spreadsheet. Each parameter was ranked and the top 3 were highlighted. Then the overall best performer was selected. The NACA 2412 met our criteria from the initial options selected as it is a general use airfoil and had the best overall performance for our use case.
From the research conducted on configurations, we decided upon a simple design that would be manufacturable given our materials. A high wing tail dragger with a conventional tail. We then compared RC aircraft across the current market to get an average wing loading and aspect ratio. Using these figures and our 100-gram weight goal, we went backwards to determine the rough size of the aircraft wingspan, that being about 500 millimeters. From there, we used this guide to size the rest of the components, and we then drew them out in scale in order to gauge the size for ourselves. We also made a 3D model using SolidWorks to help visualize the design.
The plane was made from 2 and 6 mil Depron foam. We cut out the parts and bonded them together with hot glue. To make the airfoil section, we sketched the shape on our computer, then printed it out to use as a template. They were glued to the wing skin, which was bent around them and glued on. The control rods were made with piano wire and carbon rods, held together with heat shrink tubing. We held the wings on with rubber bands so that they could easily be removed. All electronics were mounted inside of the fuselage with dabs of hot glue. The motor was screwed into the mount, then glued to the front of the aircraft. Some brief challenges that were faced during manufacturing mostly came from working with unfamiliar foam materials. At first, it was hard to cut cleanly and difficult to bend around the leading edge of the wing.
Testing our plane, it turned out to be a very lengthy process. We first started with trying a taxi in a hallway. This showed some promise, but we ended up breaking our propeller shaft. We decided that we needed to go outside. We chose to go to Carlton Gardens, a nearby park. The park wasn't very busy, but somewhat windy. We still attempted to test the aircraft, trying to taxi straight and take off. This did not go as planned. The aircraft constantly steered away from where it was meant to go and was unable to take off. After not having much luck testing outdoors, we tried and tested it indoors with the help of a tether. We set up the plane in a room and connected fishing line to the wing The plane was then flown indoors to see if it would fly. This testing method may not be the most accurate way of showing if it would fly.
After an unsuccessful session in the gardens, we tried again at the basketball courts in the city. They were more ideal, providing a flatter surface and more room to fly. It was still hard to taxi straight, constantly adjusting the landing gear tracking to solve the problem. This didn't work. On the occasion that we did taxi straight and began to take off, we didn't get much height before crashing. We thought this could be due to excess weight, so we removed the coin. This had an immediate effect, resulting in our first real flight ending in a crash. On the testing at the basketball courts, we discovered that our landing gear configuration wasn't ideal, and that our aircraft was too heavy. Our ground control issues likely came from our absence of a rudder, not being able to control the inherent nature of tail-dragging aircraft. After some additional research, it was found that tail draggers commonly have poor ground control characteristics. This meant that they required a rudder to steer the rear wheel. As we already needed to save weight, we didn't add one. We instead decided to change our landing gear configurations to one that was more stable and easier to taxi. Saving weight was quite a challenge. We had to cut out several sections of the fuselage in order to reduce the amount of foam used. We also removed the wheel cowlings and made a new, lighter wing. This got us much closer to our target weight of 100 grams. The new wing was also slightly larger than the older wing, which provided more lift. After some further analysis, we found our wing incidence angle to be lower than required. Increasing this helped increase our lift.
After a few weeks testing and improving our plane outdoors, we decided to continue testing indoors at the Bandura campus. This was not only a major improvement to the environment, but also provided the opportunity to practice at the assessment venue. The smooth floor and lack of wind made it easy to eliminate outside factors affecting the plane. The landing gear could be made to steer straight after some adjustments, and we managed to get airborne. This highlighted the uneven roll authority of the plane, which is quite common in small RC planes. Flying was also quite difficult. Testing at Bandura showed the changes made worked in our favour. It also provides further opportunities to improve the performance and controllability of the plane. Pilot skills was also discovered to be a big factor in whether or not the plane flies. During testing at Bandura, there was less major design changes and more tuning small things to improve performance. The aileron area was increased to improve control authority. Dihedral was also added to help right the plane and add some lateral stability.
As the chosen pilot for this project, I struggled a bit with the unfamiliar platform. It became evident throughout the testing that the skill of the pilot was a significant factor in the success of the plane. Lacking the experience and not wanting to completely destroy the plane, I wasn't fully committing to flying fast enough, which was partly the cause of our control and lift issues. The other control issues came from not increasing the aileron size when we increased the area of the wing, a slight oversight. Practice and confidence were gained through use of simulation software provided by the teacher. Practicing on the computer, I was able to learn how to control the plane in a risk-free environment.
Over the course of all the testing, there were several instances where repairs needed to be made. Sections of the fuselage needed to be replaced where they had been ripped off or cracks had appeared in the foam. Thin layers of foam were added to parts of the wing to reinforce them. The wing tips were damaged from scraping the ground. The rubber bands that held the wings on also had creased the frame at the wing root. The servo motors under the wings fell off a few times, so we decided to attach them to a smaller piece of foam. This was taped to the underside of the wing. Whilst protecting the frame from ripping, it also provided some adjustment to tune the resting midpoint of the ailerons. The motor mount also had to be re-glued a few times due to its poor design. It lacked a flat surface to glue to, so a new one with a flat surface was designed and 3D printed. One part that broke almost every crash was the propeller shaft. It connected the motor to the propeller. It tended to shear off when the plane crashed near the ground nose first. This was also another component that was 3D printed. The landing gear was converted to a quadricycle configuration to aid ground stability and improve durability. After removing the cowlings to save weight, we had to make some collars to hold the wheels on.
Overall, the product presented to the client was deemed satisfactory. We were able to carry 2 payloads, the ping pong ball and the dollar coin. The plane was able to take off unassisted and was controllable during flight. All in all, a successful end to the project.
Along with learning about aircraft design, I learned that design is an iterative process. No matter how well thought out your concept appears to be, challenges will still arise that will have to be worked through.
I learned that what you set out to achieve can be very different to what you end up with. Factors that you may not have initially considered can later affect the design.
What I've learned from this project is that this industry is a very complicated and fascinating industry. I've learned that the designing and manufacturing of an aircraft got me more interested in pursuing a career in aeronautical engineering.
I discovered how the testing and tweaking phase of the project can take way longer than anticipated. It was very interesting to see how one small change can make a large effect on the aircraft.